Okay, so we'll get started. Can you guys hear me?
Yes, sir.
Okay, so let's get started. In the last class, we looked at, let me just do a quick recap. We started with this particular chain of events and some results. I'll get back to this thing today. So we looked at what is known as union bound. That is, if you take a sequence of sets and ask what is the probability of the union, it's always less than or equal to the sum of the probability. This is called a union bound. Okay. Then we looked at the notion of conditional probability. That is, if you take two events, that means A and B belonging to the sigma algebra, the conditional probability of A given B is defined as probability of the intersection divided by probability of B. So this is defined only when the probability of B is greater than zero. That means B should occur with non-zero probability. And we looked at a few other properties. For example, I can write probability of union of AI given B as probability of AI given B summed over all I, provided AI is a disjoint. And we define what is known as independence. So for example, we say that A and B are independent if probability of A intersection B is product of the probabilities. Then we define what a random variable is. So essentially, it's a mapping from the sample space to R, such that you look at all those outcomes which got mapped to a number less than or equal to A. That should be an event for all A, because we need to attach probabilities to such things. So we want this to be an event, and it should be true for every A in R. Then we looked at the notion of CDF, that is fx of x, which is all those outcomes which got mapped to a number less than or equal to x. You look at the probability of that, that is defined as the CDF. So it has a few properties. For example, fx of infinity is 1, fx of minus infinity is 0, and it's monotone. And the last thing is it's right continuous, right? So that these are some of the properties. So let's go back to this. I just want to prove this thing just to get hang of using some of the axioms. For example, I would like to prove this A1 contained in A2 and so on. Let me write that in this today's lecture. So A1 contained in A2, contained in and so on. It's a chain of sets or a sequence of sets. Now probability of the union overall I equal to 1 to infinity AI is equal to limit. So let's look at this in terms of pictures. So A1 is this, what happened? Just 1 second. I think it got hung. Okay, so I'll continue here only. So this is lecture 2. So now let's look at this chain of events. A1 contained in A2, contained in and so on. So that means A1 is here. A2 is bigger than A1. That is A1 is sitting inside A2. So this is A2. This is A3. And so on, right? So you have this kind of set. So obviously the probability of the union 1 to infinity AI is nothing but the probability of the last event. The way to write this is limit n tending to infinity probability of an, right? So we deferred the proof of this particular result in the last class. So now let's look at how to prove this. Any idea on how to prove this? It's very intuitive. Is that correct? I mean, is it okay? This is definitely intuitive, right? Yes.
Sir, I think this A1, A2, A3, from these sets, we have to find out the disjoint collections.
Okay,
like,
so what
like
do you
sir,
mean by that?
like we try to define another set. Let B1 is equal to A1. Then we
Okay, so
define
let me
B2 is
write
equal
that.
to
So you are saying B1 equal to A1. Okay,
Yeah,
that's
then
this part.
then B2 is equal to say A2 minus A1.
Okay, fine. So let me just write it as A2, remove A1. Okay, this is the symbol. So let me, this is the part, right?
Yeah.
This is the part which is A2, but you have removed A1. So that is A2, remove A1, right?
Yeah. Similarly, B3 we
And
define.
so on. So we define Bn as An, remove An minus 1, right?
Yeah.
An remove An minus 1 and so on. This is the sequence. So all that I'm doing is I'm somehow converting this sequence of sets into disjoint set. That's what I have done here, right? So clearly,
sir, actually not only An minus 1, I think, sir. Hello?
What else? Yes.
Yeah, I think, sir, union I is equal to 1 to N minus 1 AI, I think, sir. An remove there.
But that will give me AI, An, right? See, what is this part? This part is nothing but A2, remove A1. What is this part?
It will be, sir, A3 remove A2. A2 only. Yeah, sir.
So let me also write this. B3 is A3, remove A2. So Bn is An, remove An minus 1 or disjoint.
Yeah.
This is also clear. Further, what else do we have? If you take the union of all 1 to n ai, that will be equal to union I equal to 1 to n bi. Well, union overall, this is nothing but an, right? Very clear. Because if you take A1 union A2, you get A2, A1 union A2 union A3, you get A3, and so on. So if you take n pieces and you take the union, you get the last piece, right? Because one is contained in the other. Okay, so this is what we have, and these are all disjoints, disjoint pieces. Now, probability of An. So I can write it in a slightly different fashion. So this is true for all n. Okay. Let me write this in a slightly different fashion. So I'll take n to infinity now. So since this is true for all n, I equal to 1 to infinity ai is same as I equal to 1 to infinity bi. Right? This is what I want. Infinity ai is probability of I equal to 1 to infinity bi. Right? Is that fine?
Yes, sir.
Okay, so now what is this? This I can write it as, let me see if everything is fine. Okay, summation probability of, okay, so I can write this in some fashion. So how do I write this? Yeah, I write this as I equal to 1 to infinity probability of bi. Why is this correct?
They are disjoint.
Because disjoint, sir.
Disjoint, right? And I'm using some axiom of probability by axiom. Okay, so now I can write this. What is a series? So it's nothing but limit of partial sums, right? Sorry, I equal to 1 to n probability of ai, probability of bi. Is that fine? Is this clear, everyone?
Yes, sir. Yes, sir.
Others? Himanshu, you have any question?
No, sir. It is clear, sir.
Everything fine? Okay.
Yeah, yes.
Okay, let's move forward. But this is nothing but limit n tending to infinity. What is summation of disjoint probabilities of events which are disjoint? This is nothing but union. Do you agree? This is nothing but, what is probability of, what is union of bi? It's nothing but
An.
This completes the proof, right? So QED. Right? Is this fine? Okay. Fine, right? Any questions? Questions?
No, sir.
Okay. Yes. Any questions? No? Okay.
So how do you write the last line? Can you explain once more?
Okay. So let me go to the last line. This one?
Yes, sir.
What is union of BI? Which is union of AI, which is
Yes.
nothing but AN, right? Because the picture, just remember the picture. So A1 is here, A2 is here, A1 union A2 is nothing but A2, right? This part, right? A1 union A2 union A3 is A3, right? So that's what we are using here. Okay.
Okay, sir. Okay, sir.
Fine. I'll keep this as a question mark. Maybe whenever you write this, you think about why. I've explained, but think about why it's this. Okay, so this was sort of something that we looked at in the last class, beginning of the last class. So now let's move on. So one of the key things that we looked at, or at least I just mentioned, is the fact that this is right continuous. Right? Yes. Who's that?
Sir, I have a
Ayush? Yes.
Yes, sir.
Yes.
Sir, according to the definition of random variable, so random variable is a mapping function, right?
Correct. It's a function. Yes.
So why do we call it a random variable then? Like variable term is why associated with it.
Just the name. So you can call it as random function also. So it's just a name. Okay. So the variable I think it's not that important to know why that name. So essentially you should know what it is, right? So it's for some reason people have called it as random variables. It's not really a variable in that sense, right? It's not like f of x where x is a variable, x changes, right? So even here, if you rotate a disk each time, whatever you observe, if you map it to a number, that varies across the experiment. In that sense, probably it's a random variable. But otherwise, the terminology is not that important. Okay, but you should know what it is, right? Mathematically, precisely, you should know what it is. Is that fine?
Yes, sir. Yes, sir.
Okay. So fx of x is right continuous. What do you mean by that? So for example, let me go back to this picture. Yes. So suppose I take a sequence which moves from the right to left, then the function value will also converge, right? This, if you look at the height, this height won't. It converges to the right value, right? So how do I mathematically write it? So you just take limit epsilon tending to 0, fx of x plus epsilon, this is equal to fx of x. This is the statement, okay? So I will leave this as an exercise. So prove, so tomorrow Savan will upload the first set of homework. So that will be part of this homework problem. So you need to show that this is right continuous. Is that fine? Oh, I'm sorry. This is 0, right? Nobody corrected this. Okay. Is this fine? So as epsilon tends to 0 and epsilon positive, okay, so you cannot have negative epsilon positive. So that means it's a sequence of positive number that converges to 0. Should be very careful. Okay, is that fine?
Yes, sir.
Okay, so now depending on what this mapping or the random variable x is, we can classify this into two types, right? One is discrete random variable, the other one is continuous random variable. So let me precisely define that, but then it's very intuitive. We say that x mapping omega to r is continuous bracket discrete if its image set is uncountable, bracket countable. Okay, what do you mean by that? So let me give an example rather than looking at this particular definition. So let's say x, so I have to define what omega is. So for example, this is the classic example, right? So a type, x of head is 1, x of tail is, let's say, -1. Okay, so this particular thing is discrete. Why? So x map countable, in fact finite set, so it is a discrete random variable. So let's look at another example. So the same thing, this example is basically 0 to 2 pi, rotating the disk. So x of omega is omega for all omega in 0 to 2 pi. So this is continuous. Why? Because the image set, so this is omega to 0 to 2 pi. So this set is continuous, uncountable, right?
Hello.
Yes.
Sir, even countable infinite sets are discrete, right?
Yes. That's why I said countable, and discrete means countable. Uncountable means continuous. Is that fine? The third example, maybe I'll just to clarify this, omega is let's say some q, right? Or let's look at even more simpler. So n, you know what this is, right? Natural numbers, 0 included. Okay, my definition of natural number is 0 included. Look at x of omega equal to omega for all omega in n. So think of it as a random variable representing the count. For example, the number of people arriving at a queue, right? That can be 0, 1, 2, 3, and so on until infinity. So this is a mapping from omega, which is n, to n. It's infinite number, but it's countable, but infinite. Is this discrete or continuous? Anyone?
Discrete, sir.
Discrete, right? So this is a discrete random variable. Okay, is this fine? Okay, so now depending on, so regardless of whether a random variable is discrete or continuous, the CDF, that is the cumulative distribution function f of fx of x, exists. So you can just blindly assume CDF. But if the random variable is discrete, there is something known as a PMF, right? Probability mass function. Right? So what is a PMF? So definition is quite easy. So I'll write it as P x of x, which is defined as probability that x equal to x. What is the meaning of this? It is all those outcomes omega and omega such that x of omega equal to x. Right? This is true for any x in real number. Okay. Is this fine? Can you give me an example of this? Somebody? Maybe I'll only ask. Himanshu, can you give me an example of a discrete, the PMF?
Binomial distribution.
Can you describe it more? I mean, what is a binomial distribution?
And the PMF of the binomial distribution is NCR.
Okay.
And P power R and 1 minus P raised to power N minus R.
Okay, what is N? What is R?
N is the number of
what is P?
N is the total number of event, and R is the trial of the event.
Okay.
P is the occurring of the event, and 1
Okay.
minus P is the not occurring.
Okay, so good. So the PMF, the example that he gave, we will revisit that in today's class itself. So maybe I'll give you a very simple example. So head type. Zero. So probability of x equal to 1. This is px of 1, which is p, which is 1 minus px of 0, which is 1 minus probability that x equal to 0. Is that fine? This is a simple example of a PMF of a simple random variable which takes 1 and 0, right? There is a name for this. This particular random variable is called what is that called? Bernoulli random variable, right? Just look at this. Is this fine?
Yes, sir.
Yes.
It's an unexpected error. I don't know what it really means. Hopefully, yeah. Fine. So let's move on. So this is what this is with respect to a discrete random variable. Maybe we will let me give you one more example. Himanshu has given an example for a discrete random variable which is binomial. So let me give you an example of a Poisson. Okay, we will be looking this particular random variable in detail, Poisson random variable. So we say that x is Poisson if, I'll write it in terms of annotation. So we say that x is Poisson with parameter lambda greater than 0. If you look at the PMF, right, x of, I'll write it as k, which is defined as e power minus lambda power k over k factorial. K can be 0, 1, 2, etc. Can go until infinity, right? Keep this in mind. So this is an example of a Poisson. So this is typically used to model, for example, the number of people arriving at a queue, or the number of electrons that got emitted from a from some filament, or it could even you can use this to model, for example, the number of packets arriving at a router, and so on. Okay, is this fine?
Yes.
Okay, so now let's look at continuous. So for continuous random variable, there is something known as probability. What is that called? Density function. PDF for short. The other thing is called PMF, right? So what is the definition of this? Well, it's fx of x. Well, x is continuous, okay? So x is continuous random variable. This is nothing but the derivative of fx of x with respect to x. This is how we define, of course, assuming that the derivative exists, right? If the derivative itself doesn't exist, then we cannot use this definition. So this is assuming that this fx of x is a nice function, whatever nice means. If it is not nice, then you cannot talk about density function. You can only talk about CDF. So we'll be happy with CDF. Yes, any questions?
So for differentiability to exist, we need to check that from left hand side also on right hand side it is continuous. So you described that the CDF is right continuous. So is it anything to do with this differentiable?
No, you should, before that, just continuity won't guarantee you differentiability, right? Can you give me an example?
Mod x.
Mod x, right? Who said that? Himanshu or no? Praveen. Okay. Mod x is one function, right? Which is continuous at 0 but not differentiable. So that means if something is differentiable, definitely it is continuous, That means it's both right and left continuous. So that is a required condition. I mean, it's not sufficient, right? So you need more than that. Do you agree?
So yes, sir. So then the function is differentiable, like the CDF is differentiable. That means it is continuous from both right and also left.
It has to be, for sure. Right. But that doesn't guarantee you differentiability. But at least it should be continuous. Otherwise, this does not make sense. Yes.
Yes, sir.
Hello.
So then the statement fx the CDF is right continuous. So sir, it should also be told that it is also left continuous.
No. So what I'm saying is, if you look at a random variable, continuous random variable, whose CDF is nice. What do I mean by nice? What I mean by that is it is differentiable almost everywhere, right? So that should be the case. Otherwise, this definition does not make sense. It has to be differentiable. That means for sure it should be right continuous, left continuous. Not even that. It needs to be more than that, right?
Yes, sir. Yes.
Okay. Is this fine? So somebody else had a question. So who was that?
Hello.
Yeah.
Sir, CDF is right continuous only for discrete random variable, or is it true for both?
It can be, in general, it has to be right. It will be right continuous.
In general.
Regardless of whether it is continuous or discrete. Okay, it has to be right continuous. But under certain conditions, for example, especially in continuous random variable case, it will be more than right continuity. It will be continuous everywhere, and not only that, differentiable everywhere. Okay.
Okay.
Okay. Yeah. So what does this mean? This means that if you look at the CDF, fx of, let's say, x, I can write this as in integral form, right? Minus infinity to x, fx of, let me use some other variable here, t dt. Okay. So what is this? This is saying probability that x is less than or equal to x. Okay. So I can interpret this in terms of this is the geometry. So for example, if you have density function like this is fx of x versus x. Now, if I pick an x, for example, so maybe I'll use t here. If you pick an x, now I want to find the probability that x is less than or equal to x. All that I have to do is basically find the area till here, right? The area will give me the probability, right? Now you might ask, well, if I take a small strip around this here, and if I find the area, what will this give us? Any idea? Let's say this point is, let's say, my new x dash, and this point is x dash plus delta x dash, small increment. So I find the area. So what do I get? This area is approximately what? The height of the curve, which is f of x dash, times the width, right? So what does this area gives us? The area gives me the probability that x falls in this small interval, right? So that means probability, it's being very, I mean, I've been very sloppy here, but intuitively this is what it means, right? X dash falling, sorry, x falling between x dash and x dash plus delta x dash. This is approximately equal to fx dash times delta x dash. Is this fine? So that means if I can interpret fx of x dash as the probability of x falling in a small interval of length delta x dash scaled by delta x dash. That's why it's called density. It's per unit length, right? That's what it says. So that's why it's called density. Okay. Any questions so far? No. So for those who are math oriented, or you guys want to look at it in a rigorous fashion. So this is something that you study at a very advanced level in measure theory. For example, there is something known as Radon-Nikodym derivative. So what it essentially says is that if, for example, you have this x, let's say, if the probability of a particular x dash, let's say, for a particular x dash is if it is 0, right? Whenever there is a jump, right, let's say the probability of x equal to x dash is non-zero, even for continuous random variable, then you cannot have a density. Okay, that's what it says. You understood, right? So you take a disk. What I'm going to do is it can take any value, but I'll put a small break at pi by 4. Okay, once in a while it gets stuck at pi by 4. Now, if I ask what is the probability that x equal to pi by 4, it will be 0.1 or 0.2. But x equal to something else, it's 0. For example, x equal to pi by 2 will be 0, x equal to x will be 0 for all x not equal to pi by 4. But for pi by 4, it could be 0.1. So your CDF could be like this. I mean, your CDF will have a jump, right? If that is the case. Do you agree? So your CDF, how does the CDF for a uniform random variable looks like? X is from less than 0, it is 0, right? X greater than 0, it will be uniform, it goes to 1 here. So this is 1. This is 2 pi. And it continues to be at 1. So this is a very nice random variable. It's a uniform random variable. If you look at the derivative, it will be a constant, right? Constant from 0 to 2 pi, 0 elsewhere, right? But suppose I have a new random variable which is almost uniform. All the values are kind of same, but probability of x equal to pi by 4 is 0.1, let's say. But x equal to any other angle, it is 0. Now, how does the fx of x looks like? It will be same, right? 0 till 0. It uniformly increases till pi by 4. Okay. At pi by 4, it jumps to. So at pi by 4, what will be the value here? At pi by 4. What is the value? Huh?
0.1.
Is it 0.1? At 2 pi, it's 1, right? That means it's 1 by 2 pi x, right? That is the fx of x.
1 by 8.
Huh? Pi by 4 is 1 by 8. So this will be 1 by 8. So at pi by 4, so this is open because it's not at pi by 4. At pi by 4, what happens? 1 by 8 is how much? It's approximately 0.128, right? Okay, so there will be a jump, right? What is the jump? 1 by 8 plus 1 by 10, right? That will be the jump. So this is 0.228, right? And then it increases linearly to 1. And it remains. So this is 2 pi. This will be your CDF. There is a jump. That means the derivative does not exist at pi by 4. So you cannot have a density of such a random variable. Okay?
So can we say that it is a uniform distribution after that?
It is uniform except for pi by 4. Okay? You can think of this as a new experiment. Okay? So the new experiment is the following. I have a nice disk which follows this. Okay? That means uniformly all the angles are possible. Okay? There is another disk. Whenever I rotate, it will get stuck at pi by 4. That means the probability that x equal to pi by 4 is 1. It will get stuck at pi by 4. Now, what I'm going to do is I'm going to take a coin. I'm going to toss it. If it is head, I'm going to pick the first disk rotate, and whatever the outcome that I get, I'll declare that. If it is a tile, I'm going to look at the second one, rotate, it will get stuck at pi by 4, I'll say pi by 4. But the probability of head to occur is 0.9. That means 90% of the time I'll pick the uniform nice disk. 10% of the time I'm going to pick a disk which will get stuck at pi by 4. Any questions? So somebody seems to have a question. Hello? Somebody has some questions? Is this clear, Rishabh? Rishabh, right? You asked the question.
Yes.
Huh?
Yes, sir.
Clear? So it's a mixture of two random variables, right? Two experiments. One is continuous because all the 0 to 2 pi, all the values are equally likely. The other disk is discrete. It only gives me pi by 4 with probability 1, right? Now, what I'm going to do is I'm going to mix the experiment with probability 0.9. I'm going to pick the first disk and do the experiment. With probability 1.1, I'm going to pick the second one. So I'm going to keep on repeating this experiment. Whatever I get, right, that will be your omega is still 0 to 2 pi, but the resulting random variable would be a mixture of discrete and continuous, and therefore there is a jump, and therefore you cannot write it as you cannot just describe the experiment in terms of your what do you call density functions, right?
Okay.
But you can do a mixture. Discrete is what? It's an impulse at pi at pi by 4, right? The other one is uniform, so you can write it as some sort of a mixture, right? The density can be written as a mixture, which is not really a density function as such, but yeah, there are some nice way of writing such experiment, writing such densities. Let's not get into that. So most likely in practice we won't encounter such a thing. Okay. Is this fine? So let's look at an example of a continuous random variable. One is uniform. I have already told you what uniform is. The other one is exponential. So I'll just write it. It's exponential with lambda. Again, lambda positive. If the density, remember, I'm going to describe this in terms of density. The density would be lambda e power lambda x for all x greater than or equal to 0. Okay, so this is lambda is called the rate or the average. Okay, is this fine? Okay.
Yes, sir.
So where is it used? For example, if you are looking at people arriving at a queue, if you look at the inter-arrival time, for example, somebody arrives now at, let's say, time t0. Someone else arrive after that person, let's say at time t1. So t1 minus t0 is random because the people arriving are random. So that difference, inter-arrival time, are typically modeled using exponential random variable. Okay. Yeah. Is this fine? Everything fine? Okay, so we will look at what is known as multiple random variables. So what if we have n random variables, right? So where do you get such a thing? For example, instead of having one disk, you have n disk and there are n people rotating. So you have n outcomes and I want to map each one of them to a random variable, right? So you'll have x1, x2, x3, x7, right? That's a simple example. The other examples could be, for example, let's say you are measuring temperature in 4 cities, right? Maybe Hubli, Belgaum, some other place, okay, and Delhi and some other place. So you have the temperature will get 4 numbers, right? I can describe that by 4 random variables, x1, x2, x3, x4, right? So so whenever you have multiple random variables, let's say x1, x2, etc., xn, I can define what is known as joint CDF. Okay, so I'll write it as joint CDF. Same story now. So how do I write this? Fx1, x2, xn of x1, x2, xn, which is defined as probability. Can somebody tell me what is the definition? Just extension of the one random variable.
So we just separate by the commas.
What does that mean?
Like, sir, nth pair, omega 1, omega 2, omega 3, dot, dot, dot. omega n such that
So let me put it this way. So there could be one underlying experiment omega in omega such that x of omega, x1 of omega is less than or equal to x1 and x2 of omega less than or equal to x2 and
yes, sir.
comma is and, okay,
Yes,
xn
sir.
of omega is less than or equal to xn. Okay, is that fine?
Yes, sir.
Do you agree? Why is that? For example, I can, so when you rotate a disk, for example, omega is 0 to 2 pi, right? So if I fix an outcome, so it's again a matter of convenience. So let's not make a big deal out of this omega thing. So I can write this as in simple short form as x1 less than or equal to x1 and x2 less than or equal to x2 and so on, xn less than or equal to xn. Okay, this is the short form, shorthand notation for joint CDF. Okay. Okay. Now, so how do we? So in the previous case, we had written a few properties. So what can you say about this? What is this?
One only.
One, right? It's easy because each event corresponds to entire omega. So if you intersect all omegas, you will get capital omega. Probability of capital omega is 1, right?
So all those random variables have the same sample space, right?
Yes. What can you say about this? There is minus infinity 1 or perhaps in multiple places, at least 1. What do you think is the answer? This is your ith place, okay?
It will be 0, sir.
0, right? Why?
Yes,
Because
because
you are asking what is the outcome that gets mapped to a number smaller than minus infinity for the ith outcome, right? Ith experiment. So that is anyway null set. Whenever you intersect any set with a null set, you get a null set. So probability of null set is 0, right? Okay. So let me look at the third property, which is sort of interesting. Again, I'll look at this. Oh, sorry, I'll do the following. Infinity, xi, infinity. What do you think is the answer? What is x1 less than or equal to infinity? It will be omega. x2 less than or equal to infinity, it will be omega. And you are intersecting all omegas here, right? Till here it will be omega. This will all be omega. This will be what? It will be xi of omega less than or equal to xi. So if this will be an event and you are intersecting omega with an event, you get the same event, right?
that event, yes, sir.
That is nothing but the CDF of the ith random variable, right? Is this fine? Fine?
Yes.
Right?
Yes, sir.
Okay. So if x1 through xn or discrete random variables, then the PMF or the joint PMF find as, okay, so let me write this. How do I write the joint PMF? It will be P of x1, xn, x1, xn, which is defined as probability of x1 equal to x1, x2 equal to x2, and xn equal to xn. This is simple, right? This is called the joint PDF. Sorry, joint PMF. Okay? Fine, right? Okay. So similarly, I can define joint PDF, right? Is defined as, so this will be f x1 through xn, x1 through xn, which is defined as, I have to take the derivative of the joint CDF, right? The nth derivative of the joint CDF, right? It is dou x1, dou x2, and so on, dou xn. Of course, we are assuming that the nth derivative exists and all that. Okay? Fine?
Yes, sir.
Yes, sir.
Okay. Okay, so we say that two random variables are x and y are independent. X and y are statistically independent if fxy of xy is fx of x times fy of y for all xy. Then we say that x and y are statistically independent. So I can define, for example, similarly, I can define statistical independence of n random variables, because I know how to define statistical independence of n events. If I have a random variables, I know how to convert that into events, so I know how to define. So this is one definition for independence. Okay. Now I also have the notion of conditional PMF, right? So what is conditional PMF? Probability mass function x given y. So I can write the conditional PMF of x given y. So let's say P of x given y of x given y. I can define it easily as what? It's the joint PMF Pxy of xy divided by Py of
EY.
right? This is something that you would have already seen, right? This is how you define conditional PMF. Okay, so when do you say that x and y are independent? When conditional is equal to unconditional, right? So px given y of x given y is equal to px of x, then we say that x and y are statistically independent. That amounts to pxy of xy equal to the product. Okay, so py of y times px of x will be equal to pxy of xy. Okay, so now we have we need to define what is known as conditional PDF. So for that we need some level of some description. So for example, okay, let me just do this first. Two continuous random variables x and y are independent if fxy of xy, you know what is the joint PDF, right? That we have defined. It's equal to marginal, assuming that the marginal exists. Then only with this definition makes sense. Okay. Otherwise, you have to go back to CDF and define it using CDF. Okay. So now, what is conditional CDF, right? So what is conditional PDF? That is something that we need to define, right? So what is conditional PDF? So conditional PDF. So these are the things that you would have already studied in your undergrad. So f x given y of x given y. How do I define this? F xy of xy divided by fy of y, right? I'll write this a little more than this. So divided by fy of y, I can write it as integral minus infinity to infinity fxy of xy dx. Okay, because if I define if I integrate a PDF with respect to one variable from -infinity to infinity, you get the marginal, right? This is something that you have to check. Okay. Any questions so far?
No, sir.
No? Others? No? Okay. So let's look at what is, so let's move on now. So we will look at what is known as a stochastic process. Well, don't worry, we won't get into the details of this immediately, but this is just one example. Okay, so what is a stochastic process? You know the notion of a random variable, right? So it's a mapping from omega to r. So what is a stochastic process? The formal definition would be this: you take xt, which is omega to r, t belonging to some index set, okay, and this is a random variable for all t, okay. Then we say that xt is a stochastic process, okay. So if this index set is countable, then we say that it's a discrete stochastic process or a discrete time stochastic process. If it is uncountable, we call it as continuous time stochastic process. Okay. Well, we will look at the examples now. So this is a very formal definition. So xt, t belonging to I is a sequence of random variables. That's all. If the sequence is indexed by uncountable set, we say that it's a continuous time stochastic process. If the index is countable, then we say that it's a discrete time stochastic process. Okay.
What is the difference between these and multiple random variable?
So whenever I talked about multiple random variables here, x1 through xn, for example, for let's say x and y, right? It's definitely a discrete thing, right? And typically, if you have a finite number of random variables, you can think of it as a stochastic process, or you can think of it as a n-dimensional random vector. So both are, it depends on how you view it. Otherwise, there is no difference. But if you consider this t, this index test set to be continuous, right? Then things are different. You cannot describe it as x comma y, right? Do you agree?
Yes, sir. Yes, sir.
Yeah. Then the index set this itself is continuously varying, right? Forget about that. Even if you look at t, this index set to be rational, right? How do you describe that? x0 is one random variable. You cannot say x.001 is another random variable, right? Because there is, for between every two numbers there is a rational. So you are missing that. So that's where the subtleties are there, right? So
okay, sir. Okay.
Fine. Okay. So I think for continuous random variable, I haven't mentioned what a Gaussian random variable is, but we will look at Gaussian in more detail later. So let's look at Bernoulli process. Let's start with Bernoulli. Any question?
Sir, I have a question.
Yes.
Sir, like you have mentioned here in the definition, t belongs to I. So t is a sequence of natural number like 0, 1, 2, like this up to and
No. T can be anything belonging to an index set I. So index set I will describe what kind of a stochastic process this is. Okay. So we will look at this example, okay, Bernoulli process, and map it to this xt, omega, r, ti, and all that. Is that fine?
Okay, sir.
Is that fine? Okay. So now I'll describe it pictorially. Maybe in the next class we will look at it more precisely. So here is the process. I'll describe the process pictorially. Okay. So here is the. Think of this as time. Okay. This is time t. Now don't get confused with. Generally, this index t, I refer it to as time. Okay. not physically it need not refer to time, but generally, that's the nomenclature. So what I'm going to do is, let's start with 0. Okay. What I'm going to do is I'm going to toss a coin with bias P. Okay. So let's assume that there is some coin with certain bias P. I'm going to toss it. If it is head, I'm going to increase this to 1. Otherwise, I'm going to keep it as at 0. Right. For example, at time 0, I'm going to toss a coin, and that coin turned out to be 0, the tail, because of which I'm not going to increment. Again, I'm going to toss. Suppose it turns out to be a tail, I'm not going to increment. Again, I'm going to toss. It turned out to be a head, so I'll increment it to 1. Okay, this is 3. Again, at 3, it turned out to be 1 more. Okay, so I increment it. For example, at 4, I toss it, it turned out to be a tail, so I keep it as it is. Okay, at 5, for example, it turned out to be a head, so I'm going to increment it. Okay, so something like this, keep on doing that. Do you agree? So I can think of this as a stochastic process, right? So this is xt and this is t, right? Why is it a stochastic process? What is happening here? So now, for example, if I take any t, right? So this is continuous, okay? So if I take a t here, right? Between 2 and 3. Now, what can you say about xt? Is it random or not? I mean, when I say random, at time t, you cannot beforehand say what is xt, right? Do you agree? Why is that? It depends on what happened here, right? For example, at 0 itself, let me look at another path. 0 itself, let's say it turned out to be a head. Okay. Okay. And then at 1 also it turned out to be a head. And then it remained at head for a long time, and then it went like this. Now, at time t, if you look at this evolution, it will be 1 here. Otherwise, if you look at this will be 2 here, right? This will be 2 and this will be 1. Right? Depending on what happened before, things will change, right? So this xt is random, it's a random variable, and it depends on what happened in the past, right?
Statistics.
Sorry?
Maybe like statistics and
well, what we are doing is basically statistics, right? Probability. Yeah. Probability is nothing but statistics. We are looking at the randomness, right? Yeah. So xt can take any value, right? So if t is somewhere between 2 and 3, it can take how many possible values? Okay, I'll write that and stop. Suppose t belongs to 2 and 3, between 2 and 3. Okay. What are the possible values? Right? It depends on what happened between 0, what happened at 1, and what happened at 2, right?
Yes.
Right? What are the possibilities? Everything can be tail, tail, tail. I'll write it as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and all the way till 1, 1, 1. Right? These are the possibilities that you have. Right? If it is all 0, it will be 0. If it is 1, this will be 2, and this will be 3. Right? Now, when do you get 1? If you have only 1 heads in 3 tosses. When do you get 2? You get 2 heads in 3 tosses, and so on. Right? When do you get 3 heads in 3 tosses? That can happen only once. Right? So there are only one possibility. Right? So the probability that this height equal to 2 is how much? You should look at all possibilities, right? 1, 1, 0, 1, 1, 1, 0. And did I miss anything? Yeah. These are the possibility. What is the probability of this to happen? P squared into 1 minus p. This is also p squared into 1 minus p, p squared into 1 minus p, p squared. So totally how many? 3p squared into 1 minus p is the probability that xt equal to 2 when t is between 2, 3. Right? So you can describe the probability. Is that fine? So with this, I'll stop. Next class, we will revisit this and try to understand it even better and more formally. Okay. Any questions? Any questions? Yes. Any questions?
Sir, no question. But sir, this stochastic processor definition, I think you just explain one more, okay, sir? In next class, maybe, sir.
Yeah, definitely. Let's go through it again. I thought I'll just
Okay,
start
sir.
it so that next time we will have some background. So just go through the book also. It's not that you should
Okay,
just
sir.
come like that and then go
Yeah,
through the
yeah,
book
sir.
and you understand it. You can ask more questions.
Yes, sir.
Any more questions? So once we describe this, then we look at expectation and things will become more challenging and interesting going forward. Okay, it won't be as easy as what we are doing right now.
Okay, sir.
Okay. Yeah. Any other questions? Chandramani, you have any
And
questions?
no, thank
No.
you. Yeah.
Raveen, Himanshu, Aish, Rishabh, Nitish, Jayant.
No, sir.
Okay.
No.
So we will upload the homework problems by tomorrow. Okay. So we will let you know what problems to solve, when is the deadline and all that. Okay. As
Okay,
I
sir.
mentioned in the first class, you are free to discuss with your friends, but typically you attempt it first. If you don't get it, try again. If you don't get it, then discuss with their friends. If you come up with an answer, don't just copy, write it in your own words. Okay?
Okay,
Right?
sir.
Okay. Thank you. Then,
Thank you, sir.
yeah, we will stop here. Thank you. Bye.
Yeah, thank you.